Hello and welcome. In this video, we're going to take a look at an application of sequences, and that is continuous compounding. Now, you all know that if you save and get interest on your savings, that your savings will more or less grow by themselves, given that the interest rate is high enough, of course. One important effect here is to save early, because the interest you got last year will already start working for you this year by earning interest on that interest. And this effect grows in the following years. So the interest you got 2 years ago has already earned interest last year. And on those combined earnings, you will receive interest this year, and so on and so forth. Now, this is known as compounding. And in this video, we're going to investigate the effects of the period that is effective for this compounding. Usually, interest is paid once a year. But of course, you can ask the question, what about if I pay interest, or if I get interest in smaller increments? So what if I find a bank that pays me interest each month instead of each year? Now, of course, the interest rate will then just be 1/12 of the yearly interest. But the compounding effect hits off a little earlier. So what you get is, if you earn interest now, then in the following month, you already earn interest on that interest. And that means the compounding will be quicker and your capital will hopefully grow more and grow quicker. One question is, how far can this be taken? Of course, we can, instead of months, take weeks or days or hours or maybe seconds. Is there a limit to that? Or would the capital grow infinitely fast if we can just find a bank that would be able to pay this interest? Now, that's what we're going to investigate in this video. So as I said, this is called continuous compounding. And again, here's the setting. So suppose you have some capital that you want to invest. Let's call that C0, the initial capital that you have, and let's say that's positive. You want to invest that at a constant interest rate. So for the sake of this application, we will assume that the interest rate is not going to change over time. And we'll denote the interest rate by R. And let's assume it'll be paid out per year first. So this initial capital will then grow according to the following formula. So what you get after the first year, after 1 year, that will be C1, is of course your original capital, C0, plus interest, and interest is R times C0. So what you get is 1 plus R times your original capital, C0. Then after 2 years, you'll have C2, and that is C1 times 1 plus R. Or you know that C1 is 1 plus R times C0, so what you get is 1 plus R times 1 plus R, so 1 plus R squared times C0. And of course that will continue. So after n years, what you'll get is Cn, and that will then be equal to Cn minus 1 times 1 plus r. Or again, if you go through all motions here, you get 1 plus r to the power of n times your original capital C0. And as I said, we're now going to look at investments that pay like monthly interest instead of yearly interest. So now assume interest is paid monthly. Instead of once a year. So it's paid in 12 periods. Over the year. With interest rate, and that is then also divided by 12. So the interest rate per month will be R over 12. Then what changes? Well, after the first year, what do we have after the first year? Well, C1, let's add an index of 12 here to indicate that we're paying that rent in 12 periods instead of just once. So that is then, again, the initial capital. Now, after the first month, you already have your initial capital plus R over 12. Then after the second month, you have your initial capital times 1 plus R over 12 squared, and so on and so forth. So after 1 year, you'll have C0 times 1 plus R over 12 to the power of 12. And similarly, after 2 years, it's 12 more months, so C2 with 12 periods per year will then be C1 times 1 plus R over 12 to the power of 12, or C0 times 1 plus R over 12 to the power of 24. And of course, this continues as well. So after n years, you'll get Cn with 12 payouts per year. So that is then C0 times 1 plus R over 12 to the power of 12n. In general, let's say we have an investment that pays in m periods per year. Now, how's that going to develop? So in general, if interest is paid in m periods per year, at a rate of R over M, then what we get is, after n years, we have our C0, and per year we get 1 plus R over M to the power of M. And now this is paid over n years, so we need to take that to the power of n, or multiply the exponent by n. So this is the same as C0 times 1 plus R over M to the power of M, and that to the power of n. And the question, of course, is now, if the total duration of the investment is fixed, we can increase that m, so we can make the payment periods smaller and smaller. What happens? Is there a limit? So that's the question that we're asking here, and that is called continuous compounding question. let n, so the total duration of the investment in years, be fixed. And increase m, so we increase the number of periods per year that we receive interest. What happens to our investment? Is there a limit to what we get? Or in mathematical terms, what we want to know is, well, if n is fixed, then we'd like to know what the limit of this term is for m to infinity. So this is the limit of 1 plus r over m to the power of m for m to infinity. That's what we'd like to know. And of course, we do know that. From our early investigations, we already know that this sequence is in fact converging, and the limit is the Euler's number, e to the power of this expression here, so r in our case. So, as we have seen, this limit is indeed something that we know. And it's given as e to the power of r. So that means Cn with m periods, as m goes to infinity, this tends to C0 times e to the power of r. So this is our continuous compounding formula. And that, of course, is a limit to the best thing you can achieve this way. So the maximum increase of your capital, if you manage to make these periods smaller and smaller and smaller, the maximum effect of compounding is this expression here, e to the power of r. And that's not small. I mean, e is 2.7 something. So that's already quite a gain that you get here from this continuous compounding effect. So it pays off to make these increments smaller and smaller, but of course you'd have to find a bank that is dumb enough to go along with that idea. If you manage to do that, please let me know the bank that you're investing with. Otherwise, I guess I'll have to continue teaching mathematics. So I'll see you in one of the following videos.